So I know a lot of us, or at least, well, some of us, were trying to improve product search using machine learning and large language models, and so is Amazon. So in our last talk today, Hajer and Praveen are talking about how Amazon is using LLMs and ML to improve product search. Thank you.
Hi, everyone. Thanks for staying around. I think this is the last session, but good news, there are vouchers for you for the drinks later. So stay with us. So I think throughout the day, we've seen that machine learnings, LLMs are integrating the whole search pipeline or search lifecycle. And the next generation product search is a reality at this point. Now in the session, we'll cover how to build these integration machine learnings, LLMs into your search engine. And in our use case, we are using OpenSearch as the search engine. So my name is Hajer Bouafif, and I am a solutions architect at AWS, focusing on OpenSearch. And with me today, Praveen.
Hello, everyone. Myself, Mohan Prasad. I'm an analytics specialist with AWS for almost 3.5 years. I'm focusing on Amazon OpenSearch service operational excellence with customers.
Thanks, Praveen. All right, let's start with the basics. What is the life cycle of a search in general? We start with data ingestion, right? In order to be able to search that data. For the data ingestion side, we prepare the data by enriching it using natural language processing techniques, computer vision techniques to capture the information from our images, for example, and then put it in the right format in order to be able to store it into your search engine. In this case, as we mentioned, it is OpenSearch. Now we have a search query coming in. The search query will go through the same pre-processing step, right? First, we need to understand what is the intention of the user on the web application, right? And I think this was the main topic of today. How can we capture the most efficient way our user's intention? So the query in itself will go into enrichment phase. We can do query expansion, we can do entity recognition, semantic understanding of the query, and this leads usually into query rewriting. Now, we'll run the search against the search engine. The search engine will take care, usually, of building the score of the documents, ranking the results, and making sure that you have the top, most relevant results at the top. You render your results to the front end, the application, and you need to make sure that also from the web application side, you display the products in the right order, let's say, in order to make it easier for your user to click or capture the most relevant document for them. Now, once we display the results, we would like to understand, are these results really relevant to our users that are using the web application? So we capture the user signals, we'd feed these user signals into post-processing step. So we train our re-ranking models. Everyone, I think today we spoke about re-ranking, and use that also as a feedback loop to provide this information as a contextual information for the next queries. And here, you do not only capture the user signals, you should also update with your business requirements. So we have two personas that we need to take into consideration. Now, in this session, myself and Praveen will go into each step, and we'll cover how you can build these integrations with OpenSearch. So if somehow you're still not aware of OpenSearch and you missed the first session, it is an open source project that recently joined the Linux Foundation. Now, from machine learning perspective and LLMs, so they usually are whether self-hosted or you are using managed services, right, in whatever cloud that you are using. And these ML models can be used to generate embeddings, can be used, as we mentioned, for NLP processing, computer vision, and also you have the LLMs. Now, at ingestion time, wherever you have text, images, usually you would process this data outside of your search engine. And then you get the results and store them into your search engine. Now, with OpenSearch, you can use ingest pipeline in order to get those documents in their raw format and use the ingest pipeline inside OpenSearch, within OpenSearch, to invoke the machine learning services or your LLM via a machine learning connector, and use the processors that are available, let's say chunking processor, embedding generation processor, enrichment processor using your own machine learning model. And this will be invoked by the ingest pipeline to pre-process the data, store them into your OpenSearch. And now at search time, the same process will go, will run. So we can also process the user query using search pipelines that themselves, they have processors that will be run at search time and process your data. For example, for hybrid search, we have a combination normalizers processor that will normalize the scores from your lexical search and vector search. And we'll cover some examples later. Also, even with LLMs, you can build your conversational search within OpenSearch in itself using the search pipeline and RAG processor. So if you have time, we hope we have a demo on conversational search. And then OpenSearch will render the machine learning-powered results into your application. And this reduces the complexity of managing any pipelines outside of your search engine, and also reduces the complexity of having multiple components and managing the multiple components separately from your search engine. That usually requires engineering teams and a lot of process to incorporate any new ingestion flow. All right, so on a high level, we have these 4 steps: query understanding, query rewriting, we retrieve the documents, and then we re-rank the results. So from my side, so I will start with the query understanding, query rewriting, and Praveen will take it for document retrieval and results re-ranking. Now, in order to understand our query or our user's intention, we need to understand what do we have in terms of document first, in order to match the user request with our data set. And that's why query understanding starts at ingestion time. So let's say if you have an image or we have a text, we can use object detection models to capture what are the objects in our images, create labels. And if we have a text, we capture the entities here. Like for example, what we have. So we have Bob ordered 2 sandwiches and 3 ice creams comes today from a store in Seattle. So we have location, we have a person, and we have time entity as well. Apologies, I think here it's not clear, like the colors, but I'm saying it out loud so you can understand what is the text in there. And here, whether for image or the text, we have enriched our documents. We capture as much information as possible from our document data set to add these labels. For the image, for example, we have a description of the image. We have the color, the category, and object. And for the text, we have the entities, as I mentioned, person, quantity, date, location, etc. Now, whether you are using your own trained machine learning model here, like for object detection or named entity recognition, you can use the machine learning inference processor that it will be called at ingest time within the search pipeline to enrich your documents and update your data set with an OpenSearch. Once we understand our data, once we make sure that we have enough metadata about what we know, will be able to apply this understanding at query time. So the query here is brown leather shoes for men under $50. She's the first one. And then we'll have the query. The query here will make sure that we apply the right filters based on the user intention. So the user is looking for a category of footwear. They are using or searching for a footwear that is under $50. So we'll apply filters across the category, price range, gender as a male, color brown. And if we have any information related, for example, location or time, we'll be able to add more filtering here. And this can come, let's say, implicitly, if we have enough information from the user, like what language are they using, or what is their current location, current time, etc. Now, if we take a popular e-commerce website, I think you all knew what's the e-commerce. So this is Amazon.com, and we apply the same query, brown leather shoes for men under $50. Now, all the results that we got from the e-commerce website, they are matching what we were looking for. They are shoes for men, they are brown, they are leather, and they are under $50. However, when we check, for example, the description here, there is no information on the price, there is no information of the fabric of the shoes. So here, if we go into details of this first shoes, for example, we see that we had filters applied against these entities. And this is done by first capturing the entities, as we mentioned, and then rewriting our query in order to filter out as much as we can the most relevant documents. This will help in reducing the computational load and will help retrieving or rewriting the query for the best matching with our user intent. Now, I mentioned about query rewriting, and we can use large language models to rewrite the queries. You can fine-tune your large language models in this case. And here we are using the LLM to write the same query that I was talking about, brown leather shoes for men under $50, and put it into structured format first. This structured query allows us to first capture the entities in the user query, and also it gives us flexibility about what type of filters do we apply really. Should we go with a strict must? Should we go with the should? Like we have, based on our business requirement, as I mentioned, you have two personas. You have the user and you have your business users as well. So we should think here, taking the structured query that generated from the LLM and apply those filters, but rewrite them into the best combination for our business use case. So here we apply a must, for example, we need to have a description matching shoes, and then we filter out the category, price, gender, color, etc. And Praveen will show us later a demo how this is built. If you want to build it yourself, we provide the GitHub example here by scanning the QR code to see how you can do that. So what we are doing in this example is that we are not training or fine-tuning the LLMs, but we are providing in few shots examples, and we are demonstrating how this structured query helps us to rewrite our query to DSL open search understandable query. And you can apply the same logic based on your search engine query language. Give you some time to scan the QR codes if needed. I think we're good.
Yeah.
All right, so there is no surprise that invoking LLMs can be expensive. And everyone who experienced it with the LLMs can confirm this. So here, we are using OpenSearch as our caching store. Usually, in order for the caching, we use exact matching lexical to compare the queries with what we have in terms of golden query sets, for example. But we can use also semantic queries. Hence the name semantic cache, meaning we'll store the query, the structured query, the original query, sorry, and the structured query generated by the LLM into, for example, if you have the data into OpenSearch, you can create another index with an OpenSearch and use it as a cache. And here we'll store the original query, the structured query, and the embedding. So whenever you have a new query, we'll run similarity search against using can and index to retrieve if we have similar queries or not. If we have a match, so we return the structured query, we will write the query based on our business use case. If not, we invoke the LLM to generate the structured query. So this does not only reduce the LLM cost, but also reduces the latency. And from our experiments, we reduced the search latency from 3 seconds into 600 milliseconds. So as a solutions architect, we also provide best practices into how to further reduce cost and improve your performance. First recommendation is warming up your cache on a regular basis. This will depend on your recency of your data, frequency of updating your queries, if you have seasonalities, etc. Warming up the cache will improve the latency, and that's one of the best practices, even when running similarity search outside of caching strategy. Also, delete the data that you do not need. Delete the old data, for example, that you know that users will not be querying. If, let's say, iPad 5, who will, like iPhone 5, who will search for iPhone 5 now? So delete the cache as much as you can, and you can use ISM, index state management policies, in OpenSearch to automate the deletion of your data based on the recency of your data. Last option is you can check also, like you can build the same caching mechanism using a framework with LangChain. They have built-in semantic cache with OpenSearch that you can check out. Now we covered query understanding, query rewriting. I give the mic to Praveen to show us how to build query document retrieval with machine learning capabilities.
Yeah, thanks, Hajer. Okay, so Hajer showed us like what are the machine learning and LLM innovations that you could do on the query understanding and rewriting part, especially with OpenSearch. So now let's jump into the next phase of the search lifecycle, which is the retrieval phase, right? And yeah, today, like as we covered all the past sessions, most of us know about the different types of retrieval. But just as a quick warm-up, we'll look at quickly on the different types of retrieval techniques. So first, broadly, we have two categories, right? Sparse retrieval and the dense retrieval. And for the sparse retrieval, we have the algorithms such as BM25 or term frequency, inverse document frequency. And we have two categories here: lexical search, the basic keyword matching technique. And the other one is a neural sparse search, which is a machine learning way of doing lexical search, where you do the term expansion and then you do the basic lexical search. And this expanded terms, you get it from the neural sparse models. We'll have we'll deep dive on this particular search later. And then we have this dense retrieval, which is based upon k nearest neighbor approach, or the approximate nearest neighbor approach. And here is where you convert your documents and queries into vector representations. And for every query vector, you're going to look for the nearest document vector and then throw them as results. And the advantage here is that you can convert your documents of different modality into vectors and then apply the same KNN search. And then we just went through this by multiple examples today. Next, we have hybrid search, and this is like ensemble way of combining multiple retrieval techniques and then do a sort of hybrid retrieval, where, like, say you want to combine keyword search and also the vector search, and then do the scoring separately, normalize the scores, combine the scores, and then do the reordering based upon your new combined scores, right? So this way you can also have your keyword search techniques plus the vector search techniques respected for a particular query. And then the last, we have conversational search, which is the retrieval augmented generative approach from the large language models. Basically, you retrieve the documents from any of the search types here, and then you send them as context to the large language model along with the original question, and then you have your large language model to generate the final answer. So this is one of the popular use case that that is used to build chatbots. We will see like how to use it in OpenSearch to build a conversational search. Okay, so let's start with neural sparse search. Having understood lexical search, like is like pretty basic, we'll jump into the neural sparse search. So basically, on the ingestion side, say if you have a document, something like Apple products are expensive, you're gonna use the ingest pipeline. Like as Hajer explained, this ingest pipeline is going to make it easy for all the machine learning integrations, right? So this you're gonna use the ingest pipeline with sparse encoding processor, and this sparse encoding processor will be responsible for converting this particular document into the token weight pairs. Okay, and this is given by the neural sparse models, and these models like either like they are inside OpenSearch or it can be hosted somewhere outside of OpenSearch, say like SageMaker. And then as you see here, this token weight pairs like add some semantics to your document, right? For example, for this particular document, you see the higher weightage is added for the words like technology and Mac, whereas the tokens like fruit, the apple foods are like given lower weights, right? So that is the way it adds semantics so that it is able to differentiate the apple fruit versus the apple technology, right? So you get this automatically from your sparse encoding processor, and you add these features, and then they get ingested into the OpenSearch inverted index. And then on the query side, you have this OpenSearch query type called neural sparse query, which will do this conversion again for your incoming query, right? So for example, here for the Apple headphones, neural sparse query will talk to the sparse encoder model and then convert them into vectors and then do that dot product against the document features. In addition to this, you can also add the search pipeline for your neural sparse query with the sparse two-phase processor. This is one of the recent feature that our service team added. So here, basically, what happens is the neural sparse search happens in two phases. So basically, first there will be a threshold that is like an input from you as input parameter from you. Say you say, okay, only retrieve the documents, top documents by matching the tokens here, whose weights are greater than equal to 0.5, for example. And then you retrieve the documents based upon this particular filter, and then re-rank those documents only with all the tokens considered, even the lower weight tokens. So this way you could reduce the number of dot products that's happening. Instead of considering the all list of tokens, it will be just doing the dot product and retrieve the documents based upon the token weights with greater than 0.5. So you are basically trying to reduce the dot product, but still considering the lower weight tokens only on the re-ranking phase. This is one of the improvements that is giving better results than the version 1 neural sparse search. So not only on the search side, but also with respect to the models. Like last year, we had this OpenSearch sparse models V1 released, version 1, and we had the 3 variants of models again. And like one of the challenges I would say with those models was like the size, the number of parameters that these models were trained with. They were like decent in quality, but because of the size of those models, the ingestion throughput and the search latency metrics were like facing some challenges. So recently, last month, we had this OpenSearch sparse models V2 released, and these models, like the size of these models, were drastically reduced in the number of parameters because these models were trained by the knowledge distillation process, having the teacher-student model training approach. And as a result, we got 3 models again, the distilled version. The first one is the bi-encoder, where you use it for both the queries and documents. And the second one is the document-only distilled version of the model, which is like only for the document side. You just do the feature expansion for your documents, and then for the queries, you don't do it. And we also had this mini version of the first 2 models to even improve latency, but with the trade-off in accuracy. So all these models are open sourced and available in Hugging Face at this particular link. So on the benchmark side, like there was like an experiment conducted to see what is the performance of these models compared to the sparse models V1. version 1, and there were like the ingestion throughput, search latency. We got improvements in these metrics without compromising anything on relevance, because the NDCG at 10 on the beer data set was calculated, and it was approximately same for the sparse models V1 and the sparse models version 2. So yeah, now the models are reduced in size without any compromise in relevance, improving your throughput and latency metrics. And the details of that particular benchmark is in this link. Okay, so on the dense search, so here we have the ingest pipeline text process with text or text image embedding processor based upon the multimodal nature of your documents. Basically use this processor to convert your documents, multimodal documents, into vectors by talking to the dense embedding model sitting in, say, like in the OpenSearch or outside OpenSearch. And then on the query side, again, you have your multimodal query. You use a neural query, which is going to convert this particular multimodal document into one single vector representation. And finally, you hit the KNN search to get the results automatically. So like most of the things are done within OpenSearch. You don't have to do it on the application side. And this link takes you to the complete notebook, which takes you to the process of fine-tuning the embedding models. Because as we learned enough that fine-tuning vector embedding models is going to perform well instead of using off-the-shelf Hugging Face or open source embedding model. So like in this particular notebook, we first have a fine-tuned LLM, which is used to generate synthetic corpus like the triplets. And these triplets are used to train a sentence, fine-tune a sentence transformer. And then that would give you the fine-tuned embedding model that you could put inside OpenSearch or host it somewhere outside OpenSearch. So this takes you to the detailed process of how to fine-tune the vector embedding models for your domain terminology. Yeah, the next is hybrid search, which is getting more popular. So you do different types of scoring. For example, here BM25 scoring, KNN scoring, and then you normalize the score separately. And then you combine the scores, say by using a weightage. For example, you want to have 0.3% of keyword search score and 0.7% of your question similarity score. And then you re-rank your documents based upon that new combination of scores. So this is in general all the steps for hybrid query, but hybrid search. So with OpenSearch, search pipeline, normalization processor, you have to just like tell what is the weightage that you want to tune and what is the combination normalization technique that you want to use. And then that's it. Like, so you just use a hybrid class and then you apply this search pipeline, then everything is taken care by OpenSearch itself. So you don't have to do this list of steps that is listed here. The last search type, the conversational search here, like, as you know, to build a conversational search application, say a chatbot, there is a lot of moving parts, right? Like first you have a question and then you have to convert that into an embedding model, and then perform a KNN search or any other retrieval that you're interested in. And then you get the documents. In addition to those retrieve documents, you also have to look up, is there any history of conversations that is related to this new question? Then you have to also include those documents that happened in the previous conversation. And then you fine-tune your prompt and send it to large language model for it to throw in response. And this is going to happen for every turn of conversation with the user, right? So with the RAG processor, search pipeline, this is all abstracted from the developer. So you just have to do it, configure everything in the RAG processor once, and OpenSearch will be able to just do all these steps listed here, even looking up the memory index to store the history of conversations and do that automatically. So yeah, so we talked enough about result re-ranking, which is the last phase in this search lifecycle. And yeah, like the popular approach, the cross-encoder, using the cross-encoder models to re-rank your results. Yeah, like we have in OpenSearch, we have this search pipeline with the re-rank processor, which is gonna do this automatically for you, which is retrieving the documents, talking to the cross-encoder model, get the new scores, re-rank the documents, and then throw the re-rank documents out. So you just have to use the re-rank clause along with the main query, and with the search pipeline, it's gonna do it automatically, like by talking to the model wherever it is sitting. Okay, so yeah, so we had multiple examples today on using judgments to train your custom models that could be used at the retriever and the re-ranking phase. So first, like to get your judgments, one of the straightforward approaches is using explicit feedback, right? Say you have your search team or your group of people who's gonna annotate your popular queries as relevant and non-relevant, and then you can use that subset of human annotated set to fine-tune a large language model, so that this large language model will be knowing to evaluate your popular queries, telling that's relevant and non-relevant, or even graded labels, and then you can use this combination to derive your judgments directly. But still, like this involves aspects of cost and also scaling, right? Like human and also the fine-tuning large language model might get complex. So that's where like we have getting the implicit signals from your application, like based upon user interactions, captured through OpenSearch UBA. So OpenSearch UBA is going to have these two different indices, like our colleague Ashwath, dived into details this morning. But yeah, you have your application, you have your plugin in the application side, and then it's going to throw out all the events and queries, and then you're going to log it into your two separate indices in OpenSearch, and then you have your implicit signals converted to judgments. Once you have your judgments, then you can think about training custom models both for your retriever and the re-ranker. For example, like for on the retriever side, you can have a training for learning to boost model, which we are currently experimenting. So basically, this learning to boost model will throw you out weights, terms of like what weightage of lexical search and what weightage of vector search could be a good combination for this new query. So basically, it's like you're dynamically selecting your retriever type, because we covered, like there are different search types, right? So we have this LTP model to throw out the right weights for your hybrid search, and then you do the dynamic retriever selection, and then use that dynamically selected retriever as for the online search. And on the re-ranking side, we can either use learning to rank model or personalize to be trained from those judgments, and then have this rescored results out of these models. And one advantage here is that you can use OpenSearch re-ranking plugins, because we have Amazon personalize and LTR models strictly tightly integrated with OpenSearch re-ranking pipelines. So with that, I will give it to Hajer for a quick demo on the conversational search with OpenSearch.
All right, so we have a few minutes. We'll go to conversational search demo, and then if you're interested, we can demonstrate how to rewrite the queries using LLMs. I think we only have 3 minutes left. All right, so here we are using DevTools in OpenSearch dashboard to create the conversational search using the RAG processor in search pipeline. So the first step will be to enable the settings of the cluster, to enable the memory feature that will store the conversational history of your user. So the question and the responses, and we also enable the RAG pipeline. Next step would be to create the ingest pipeline. So the ingest pipeline, as you see here, we are actually creating text embeddings from our data. So we have the model ID there that is hosted in Amazon Bedrock in our use case. And then we map the original text content into the field that will host the embeddings called text content embedding. Next, we'll need to create the index. Yeah, I think I already have it there. So let's delete it first. So the index here, something to be aware of. So we enable in the setting the index with type canon, of course, and we also say that we want to use the ML ingest pipeline that we just created in order to generate the embeddings at ingest time whenever we have new documents. And then in your mapping, so you have your original text field, and then you have the canon vector type of field to host the embeddings. So quickly we'll ingest some data samples. So this data is actually we captured some data regarding the different search types that are supported in OpenSearch, and we'll ask some questions regarding that. So an example of how a document looks like. So I just ingested the text document, right? And we see here in one example of a document, we have the original text and we have the generated embedding. Now, in order to run the conversational search, we mentioned that we need the search pipeline. So here we create a RAG pipeline. We define the processor of type retrieval augmented generation processor. We define the model ID or set the model ID, which is the LLM in our use case. And we define the system prompt user instructions that you can customize basically for your prompt engineering. So I created the search pipeline. Now I'll create a query, a memory that will host the conversational history. I will take this memory ID so I can use it later. Now we'll start with one question. So here is the search query. At search time, we include the search pipeline. We mentioned that we would like to use the RAG pipeline at search time. And then we are using a neural query to run similarity search using the text embeddings. We define the same embedding model at search time as well to generate the embeddings of the text. And then we call the processor generative RAG processor with the different parameters, including the LLM model, memory ID, context size, message size, and timeout. These settings are regarding like how much of messages or like text question and answer we would like to store in our memory. So I copied the memory ID earlier. Let me paste it here. And the first question will be, what is neural sparse search with OpenSearch? Here we are using an old version of Claude to run this experiment, so bear with us. It takes some time. And here we see the generated answer. So we have the hits, we have the context, and we have the generated answer from the LLM under the retrieval augmented generation processor with the message ID that we'll see later in the memory. So we see based on the search results, which is the context, neural sparse search is an open search, alternative to semantic search, the rest of the generation. Now the second query will be a follow-up query. How is it different from semantic search? So here we expect the LLM to understand that we are talking about, if you're following, neural sparse search. Let me copy the same memory ID here. And we'll run the follow-up query. And then we'll check the conversational history for that memory ID, which let me update from now. Okay, checking the results. Let's hide the hits. And now from the retrieval augmented generation generated answer, we see that it understood that we're talking about neural sparse search. And here it explains the differences are both neural search methods and open search that aims to improve the search relevance. And using the memory feature, indeed, this is how we were able to ask this follow-up question, and you can customize basically the memory settings, how much messages you would like to keep. And now we can check also the different messages, query, and question and answer generated asked by the user using that memory information. So this is how in few API calls in DevTools, you were able to build a conversational search with OpenSearch. I think we're on time. Okay. So thank you, everyone. And wish you a good continuation of Haystack.
Thank you, Hajer. Thank you, Praveen. Questions from the audience? There.
Sorry for making it hard for you. So this question is about the cache. You talked about the cache, which helped you get your latency down from 3 seconds to 600 milliseconds. It's a technical question. What if it's not an exact match of the query, but it's very similar to the query? How do you decide to retrieve a similar query, which is not an exact match from the query which the user typed from your KNN index? Of course.
Yeah. So first of all, for having the semantic cache, like you should think about considering all your popular queries. So right? So what is going to be your most used queries, most frequent queries from your search log. So that should be your first way of hitting the LLMs and storing them as cache. So coming to this second point where okay, so first you do the exact match and something is not matching. So, and then what you have to based upon say the match is not happening in the exact search, exact lexical search, and then you do the similarity search. But for this similarity search, say you are seeing whether there are any more similar queries for this particular query, so that I don't have to hit my LLM again and then just retrieve the already extracted filters from the memory. For this case, you should experiment with proper threshold values. What is going to be the threshold value, so that you consider this is going to be a probably already, probably a good similar query that you could that you could derive directly from the cache instead of going to the LLM. So experimentation on that particular threshold is where you decide, okay, whether I'm going to use this use this result from the semantic search, or am I going to go to the LLM directly again for the another hit and then store it back to the semantic cache. So yeah, it all starts with your popular queries, and based upon that, you learn your threshold values and set your threshold values to see whether to hit the LLM or use that particular thing from your KNN index.
Okay, we have a question from Mateusz. He's interested in your experience with the latency of the search. I think 600 milliseconds were mentioned, and he was wondering if that is the latency that your customers typically face, or what these 600 milliseconds were relating to.
No. Yeah, go ahead.
That was related to our experiment. So we are not really building all best practices there. So in our experiment, we did basic indexing and search. We hit 3 seconds, and then with this caching, we were able to reduce to 600 milliseconds. But you can definitely go lower than that if we review all the best practices that you need to implement for search latency. Praveen, if you
yeah, just to add that 600 milliseconds came from that is the when there is a similarity search. First, it does an exact search. There is no match, and then it goes to the similarity search, it passes the threshold, and then the result is out. So that's where that 600 milliseconds, 3 seconds was down to 600 milliseconds. But if there is an exact match, then it's gonna be even down, even below from that 600 millisecond. And again, this is on the CPU setting for our data set samples, for our demo data set. Yeah, so that was basically on a demo experiment stuff.
Thank you for a good talk. You showed us, like an architecture of the whole thing, which is quite standard, query understanding, retrieval, re-rank. I'm wondering how much of this experiment is feeding into the dog food for UBI. Yeah, so for example, if you think of such a system, usually, there will be different stakeholders who are responsible for optimizing query understanding. There could be different, and there could be some overlap, like, optimizing query understanding quality, optimizing retriever, latency and quality, optimizing re-ranking, and so on. How much of the so, for example, in today's earlier talk about UBI, I didn't see much of the, the internal bit, the interfaces between the query understanding and retriever, for example, or the retriever and the re-ranker, the information, the signals, the, what these subsystems work on. how are they capturable in the schema that UBI is building? And are you guys feeding into that?
Okay, so I can just talk about that retriever part. For example, the schema, whatever morning you saw, that's the standard one. But say like for you, if you want to build a model that you want to use it in your retriever side, for example, like a learning to boost model, and then for this, like what we are trying to do now is like take the queries, whatever is stored in the query index, and then see if that wasn't that was a hybrid search where you have multiple queries in that, and understand what was the weightage used there. So that's all like you do, like you understand what should be done from there, and then you take the queries, you do the processing, you do the sort of building the training data set from that particular query index. So it's not something like you get ready-made for your schema. It's like you decide, okay, I want to have a learning to boost model, so let me see what are the weights in different fields, what are the weights in different subqueries that in the same query, and then you train a model. So it's like this is like you, based upon your requirements, you take that and then do the further processing, and then based upon that further processing, you project that data as features into the model. So it's just the same. So you do the further processing from those queries and events, especially queries on the retriever side for a learning to boost model in case.
Okay, thank you very much. I think we're at time. We have more questions, plus, so please approach Hajer and Praveen directly. Yeah, thank you very much for your talk.
Thank you.